So we've done the intravenous flow rates, and we'll come back to that if we have some more time. But I want to start looking now at dosages based on weight. We had that discussion several weeks ago of the difference between weight and mass, so I'm not going to get into that again. We've accepted that kilograms, even though they are technically a unit of mass, get used as a unit of weight. So when we're looking at dosages based on weight, we might have a label that, or an order that says, to follow the label on the bottle where the label says 200 milligrams per kilogram per day. And the order says to divide that out to be administered over 4 doses a day. What would that be, like QH6 or Q6H or something like that, every 6 hours? I'm not going to get into medical abbreviations because I will mess them up. So we'll just say divided up over 4 doses per day. So how much is going to be given per dose? If the bottle also says that this is concentrated as 25 milligrams per 2 milliliters. And our patient walks in the door with a weight of 154 pounds. Well, the first thing we run into here is the fact that the label is given in milligrams per kilogram, and our patient's weight is 154 pounds. So the first step in these problems is always to make sure the weight is in kilograms. And to do that, we could go through a unit conversion, but it's really simple. You just end up taking your pounds divided by 2.2 to get your kilograms. So 154 divided by 2.2 is going to give us 70 kilograms. So once we have our weight converted into kilograms, the next step will be a proportion. This is a multi-step process. Some steps involve one step involves a proportion, and the other steps go back to our unit conversions or dimensional analysis. In our proportion, we can't have 3 different values, so we have to pick one of them that we're going to leave out. We usually leave out the time frame. We make sure we have it noted because it is important. We will need it, but we can't include it in our proportion all at once. So we're going to start out just simply with the 200 milligrams per 1 kilogram. Keeping in mind that this is a dosage that is spread out over 1 day, so that information doesn't get totally lost. Now over here, what other information do we have to put into this? We have the 70 kilograms. So I put our 70 kilograms in here. That's our patient's actual weight. And we're going to cross multiply and divide. 200 times 70 divided by 1 is going to give us, what, 14,000 milligrams? Look right? So we know that this patient is going to get 14,000 milligrams. Well, 14,000 milligrams per what? Per day. So that time does come back into this. This is still per day. Now, of course, this being a liquid medication, apparently, we have the milligrams per milliliter on our label. We have to convert that into milliliters now. So I have 14,000 milligrams per day. How many milliliters is that going to be per day? So milligrams will go on bottom, milliliters on top. 25 milligrams per 2 milliliters. So the milligrams will cross cancel. What is that? 1,120, does that sound right? Milliliters per day. Let me do it. 14,000 times 2 divided by 25. Yes, it is 1120. I skipped a step. You can multiply that out to get 28,000 milliliters per 25 days and then divide by the 25. I just kind of did that all at once right there. Everybody see where the 1120 comes from? Any questions on that? Okay. So that leaves us with one last step. It's 1,120 milliliters per day. We were told to divide this into how many doses? 4. So we're just going to divide that by 4 to get 280 milliliters per dose. So let's take a look here. We're going to look at a label that says 800 micrograms per kilogram per hour. Constituted as 5 milligrams per milliliter. Patient weighs over 220 pounds. You guys tell me, what's my first step? Make your weight. So you're going to divide by 2.2 to give us 100 kilograms. Then what? Okay, oops, that should be micro, not there. It's 800 micrograms per 1 kilogram. And then $100 kilograms over here. Cross multiply and divide. We're going to get 80,000 micrograms to this patient. Now that is per hour, but we have another conversion to make. This is constituted as 5 milligrams per milliliter, so we have to convert this into milligrams. Now I really don't have to do an official conversion to get from micrograms to milligrams. Micrograms to milligrams is going to be a factor of 1,000. Those are ones, remember I mentioned you should get good going from grams to milligrams to micrograms. Each of those conversions is moving the decimal point 3 spots. Is a milligram, if I'm going to milligrams here, is a milligram bigger or smaller than micrograms? Milligrams bigger, so the number has to get smaller. 3 decimal places leaves us at just 80 milligrams. Bless you. So now we're going from that 80 milligrams. Is there anything else attached to that 80 milligrams? Yes, it's per hour. Now, we didn't have that in our proportion, but it is still there. So it is 80 milligrams per 1 hour. And it was 5 milligrams per 1 milliliter. So the milligrams are gone. It's now 80 milliliters per hour. Or per 5 hours, I should say. Or 16 milliliters per hour. This one didn't specify what the length of between doses is, so we're just going to leave it at 16 milliliters per hour. Now, sometimes with these, you're given a range. For example, let's say that you look up a recommended dose. And it says from 9 to 12 milligrams per kilogram per day. let's say that it is also the bottle says it is constituted as 5 milligrams per 2 milliliters. And you have a patient that, let's put him at 187 pounds. Find the range of acceptable doses. First step, of course, is still going to be what? Find the weight. Divide by 2.2, which is going to give us 85 pounds. That's good. Or 85 kilograms, I should say. So our patient's 85 kilograms. What's next? So we're going to have to pick whether we want to use the 9 or the 12 first. Doesn't really matter which one, you guys pick. The 9. Okay. So 9 milligrams per kilogram is where we're going to start out. And of course 85 kilograms goes here. Cross multiply and divide. 9 times 85 divided by 1 is, what, 765? Sound right? Perfect. Now, of course, we still have to go back to our unit of time, which was per day. So that is 765 milligrams per day at this point. What's next? Have to convert to milliliters. So we got our 765 milligrams per 1 day. We're getting rid of milligrams, so milligrams go on bottom so they cancel out. And we said 5 milligrams per 2 milliliters. So milligrams cancel. 2 times 765 is 1,530 milliliters over 5 days, which divides out to give us, what, 306 milliliters per day. Is that the minimum or the maximum dose? Minimum, because we use the smaller number. So this is the minimum dose. Now to find the maximum dose, we could go back and use the 12 and do that calculation again. I don't feel like going through that amount of work. There's a process called the titration. In a titration, what you can do is, as long as everything in the problem stays the same except for the dosage by weight, or the amount per pound, or per kilogram, I should say, all you need to do is have the new amount over the amount that you used before. So what that means is for this, to change this from the minimum to the maximum, this is 306 milliliters per day. We're going to multiply by, we used the 9 before. We want to convert it to the 12. So all this is saying is we're going to take the 306 milliliters per day times 12 and divide it by 9, pretty much. Which is going to give us, what, 408 milliliters per day? What do you think? Not so bad? Yeah, it's a lot easier to do the titration than it is to redo the whole calculation. Let's say the doctor orders 10 milliliters of Tylenol 3. Every 4 hours. For a patient who weighs 44 pounds. Before you administer the dose, you want to double check it. And so you look at the label And the specs for Tylenol, for medications, I should say. On your label, it says that there are 12 milligrams of codeine per 5 milliliters. You look up and you find that the safe amount of codeine is 0.5 milligrams. There it goes. 0.5 milligrams per kilogram every 6 hours. So when you go to double check your dose, what just happened here? There. My computer decided to act up on me today, apparently. So you want to go to double check this dose. So what we need to do is we need to look at, for this patient's weight and whatever the safe dosage is, we need to figure out what that maximum safe dose is and see if we're under it. So we're going to start out still with the patient's weight. 44 divided by 2.2 gives us 20 kilograms. And then our next step is still the same. Looking at the label here is 0.5 milligrams per kilogram. How much is that for 20 kilograms? Well, that'll come out to be, when we cross multiply and divide, it'll come out to be 10 milligrams. So now we have that 10 milligrams. This says is safe every 6 hours, right? We're going to convert that from milligrams into milliliters. 12 milligrams goes on bottom to 5 milliliters. So that's going to give us, the milligrams first cancel. 10 times 5 is 50 milliliters. 6 times 12 is 72 hours, which is going to divide out 50 divided by 72, 0.69. So 0.69 milliliters per hour. So now the doctor's dose is every 4 hours. So if this is 0.69 milliliters in 1 hour, we have to go back to a proportion to make it for 4 hours, which is going to give us, what, 2.76 milliliters? 78? 2.78 milliliters over 4 hours. What's that tell us? That 10 milliliters is going to overdose this patient on codeine. You got 2.76?
I did, yeah.
You didn't. You must have left the number in your calculator and didn't round it off.
Yeah.
Yep. Yeah, the doctor's trying to kill the kid. That's one of the ironies about being a nurse, is even if the doctor screws up the order, you still have to catch it. Okay, so let's look at another one. Let's say that a doctor orders, and we'll stick with a similar medication. Let's say the doctor orders 8 milligrams every 6 hours. So look at the label on the bottle, and the label says that the concentration, or not milligrams, milliliters I should say, 8 milliliters every 6 hours. The label on the bottle says it is constituted at 10 milligrams per 3 milliliters. And you look it up, and the safe dose is 2.5 milligrams to 3 milligrams per kilogram per 8 hours. And this particular patient, oh, what did I put in here? Oh, let's just say that this patient here weighs 99 pounds. So what's our first step here? Figure out if this is a safe dose. We're weight conversion. Divided by 2.2 gives us 45 kilograms. Okay, what's next? Well, if we're looking at safe dose, we would probably want to do the maximum one first, right? We could do the 2.5, but let's do the 3. Because if the doctor goes a little too low, that's not near as important as if the doctor went too high. We'll still come back and find that minimum dose. That's 3 milligrams per 1 kilogram. So how much is it per 45 kilograms? Cross multiplying and dividing, we get 135 milligrams. Now, once again, that's 135 milligrams per 8 hours. Very good. Now what? Now we have the 10 milligrams per 3 milliliters. So we're going to make that conversion. So milligrams will cancel out. 135 times 3 is 405 milliliters. 8 hours times 10 is 80 hours. We divide that out, we get 5.0625. Is that right? Is that correct? Perfect. So 5.0625 milliliters per hour. Now, the doctor's order was for every 6 hours. So that means we're going to do a proportion to get that to 6 hours. So 5.0625 times 6 ends up being basically, what, 30.37, something like that, milliliters. So there's definitely not too much medication being administered here. That would be the, of course, this is the max amount since we used the larger number. Let's find the minimum amount. To find the minimum, we're going to take the 30.37, and we use the 3, and we're converting it to 2.5. Oops, I did that wrong. The 3's going to go on bottom. Well, we used going to go on bottom. 3 and 2.5. There we go. I was at 25 point what? So 25.3 basically. Milliliters. That's every 6 hours again. So basically this doctor's orders, while not harmful, probably too small to be effective. Any questions?
What did you do at the end there?
I just did the times 2.5 divided by 3. The titration can also be used for adjusting time. Let's say that you've done a calculation and you found that the safe dose is 18 milliliters every 6 hours. And your doctor has said to administer a dosage every 4 hours. See you guys next week. Remember, test next week. You bet. So the doctor is said to administer the dosage every 4 hours. How do we adjust that dosage to be the same amount, just spread out every 4 hours instead of every 6? Well, since the time span is shorter, it would make sense that the dosage will be smaller, right? So we still use a titration rated to the 4 and the 6 hours. To make it smaller, we put the smaller number on top. So 18 times 4 divided by 6 is going to be 12 milliliters. And if you were to figure that out the long way, you would find that, yes, 18 milliliters every 6 hours is equivalent to 12 milliliters every 4 hours. Okay, the next step, last step. Dosage is based on body surface area. A couple of areas where body surface area is the determining factor on how much medication to give. Skin conditions, eczema, stuff like that. Burn patients. It's important to deal with body surface area calculations. I'm going to show you 2 ways to do it. One, in fact, I got to find it here. One way is kind of the cheater way, which is this chart I'm putting here. It's in your book. I think it appears in there a couple times. I know it's on page 192 in your book, at least once there. I think it's on another page, a page or two later as well. This is called a nomogram. The nomogram is just a pictorial way or a graphic way of estimating body surface area. Now, there's actually 2 different charts on here that are kind of wrapped in together. First of all, you have this table in the middle here. And that is for children, small children of normal height and weight. In other words, height and weight proportional. You can just use their weight to find their body surface area. And this is in pounds. Body surface area, by the way, is always given in square meters. The second chart then is everything that's outside of that yellow box, where we have the height, we have their weight, and then the body surface area is determined in here. And the way you use the nomogram is you actually draw a line connecting their height to their weight. So you'd find their height over here, you make a dot, find their weight over here, make a dot, you draw a line connecting them. Obviously, your line has to be straighter than the one I just drew. And where that line crosses this little axis right here, that would be their body surface area. So let's do some examples to show you how that works. So let's say we have a patient. That is 49 inches tall and weighs 92 pounds. So we go to our chart. 49 and 92. So height in inches, 49 inches. You're going to find... Now the scales on this change as you go up, by the way. You can see here, you got 12, 12 and a half, 13, 22, 20, but now then the halves disappear and it goes 20, 21, 22. It just gets tighter and tighter. The scale changes as you move up, so be very careful with that. So now up here, 49 inches tall is right there. We said a height of 92 pounds. So, oops, I'm sorry. You're right. Thank you. That would be 44. You're right. 49 is up there. Thank you. Sorry. Some days the little hamster doesn't go completely on the wheel. He just sits beside it and tries to spin it with his paw a little bit. Not quite reaching full speed today. So the weight was 92 pounds. So 92 pounds. Here's 90. There's 100. We have to do a little bit of a guesswork here. Because it's 90, 95, and 100. So 92 is going to be slightly closer to 90. So somewhere in there. And obviously this nomogram, no matter how we use it, is going to be a slight estimate. So now we need to connect those with a line. I'm going to use my draw tool so I can actually make a straight line here. So from there to about there. That line's a little bit light. Let me darken it up for you a bit. Don't want to make it too thick because then it's hard to... So there's the line. So where the line crosses here, crosses this axis is where it's going to be defined. So we look at that. Well, that's 1.2, and that's 1.3, so it looks like it goes up by 0.2 or 0.02. So 1.22, 1.24. It looks like it's right between 1.24 and 1.26. So I would call that 1.25 meters squared of body surface area. You can also use this chart, by the way, to tell if a child is height and weight proportional. They're 92 pounds, by the way. 92 pounds would have put them slightly off the top of this chart. But you can see here 90 pounds is more than 1.3 square meters. This kid's a little bit light for his height. So anyway, back to here. The nomogram works. I don't care for it much, but it works. You're welcome to use it. I prefer, since I'm a math geek, to use formulas. The first formula is if the person's stats are given in metric. So if the height is in centimeters and the weight, of course we know it's not really weight, but it's mass, is in kilograms. So the body surface area in square meters would be given as the square root of height times weight divided by 3,600. Now that last patient was in inches and in pounds, so this formula isn't going to work for them. But let's take a new patient. Let's say we have a patient whose height is 120 centimeters and their weight is 35 kilograms. So you can put them into this formula, 120 times 35 divided by 3,600, and then square root. Now depending on your calculator, I'm looking around the room, it looks like most of you have calculators that are two-line displays, so you can enter this all at once. You would hit second square root to get the square root symbol in there. And then you would just type 120 times 35 divided by 360, or 3,600 I should say. Hit equal. Many of you, by the way, will have to close parentheses at the end of that before you hit equals. I'm getting 1.08 square meters. Everybody come up with that? Everybody get something different? I'm on your calculator. You have to hit that second and then square root key, right? And then you'll get something that looks like this usually with the parentheses there. So you'd have to type in the 120 times 35 divided by 3,600. Then you have to close the parentheses before you hit equals. So you get 1.08 meters squared. Everybody get to work? Cool. So that's if everything's given in metric. If things are given in standard, in other words, heights in inches and weight is in pounds, well, then the body surface area, still in meters squared, is going to be the square root of the height times the weight divided by 3131. Why is this number here different? Well, that's just the conversions between inches and centimeters and pounds and kilograms. So let's go back to that previous patient who was 49 inches and 92 pounds. So we'll do second square root. 49 times 92 divided by 3131. And again, most of you have to close your parentheses. 1.199, so 1.2. We were getting 1.25 on the nomogram. So we weren't doing poorly by any means. To me, this formula is simple enough that you don't need the nomogram. Back in the days when you had to calculate it out by hand without a calculator, then the nomogram was useful. So let's check a couple here. Let's say we have a patient who is 180 centimeters tall and 125 kilograms. So nomogram, we can go up to 125. No, it doesn't. So this one, if we were to go and to put this one on the nomogram, it goes up to the 180 centimeters tall, but it does not. It only goes up to 80 kilograms. So this one here is going to be kind of we wouldn't be able to do it on the nomogram at all. So we have no choice but to stick with our formula. So it'll be 180 times 125. 3,600 or 3,131? 3,600. Very good. Giving us 2.5 square meters. Okay. How about a patient who is 56 inches tall and weighs 140 pounds. So it'd be 56 times 140, and this one would be 3131 because it's standard units. Giving us 1.58, it looks like. Let's double check this one on the nomogram. So 56 inches, 140 pounds. See if we get close to it. So 56 inches is going to be right there. 140 pounds, about there. Well, you can see it's giving us like 1.625. So the nomogram, and this has been my experience in the past, so the nomogram almost always gives you a little bit higher than the formula. I like the formula anyway. I'm a math geek though. So anyway, let's say that the doctor orders 40 milligrams of hydroxyzine. For a child 88 pounds and 44 inches tall. You look it up, the recommended safe dose is 30 milligrams per square meter. So is this a safe dose? So first step, let's find the body surface area. So 88 times 44, or 44 times 88, doesn't matter what order we do those in. Divided by 3131, very good. So what do we get? 1.11. So okay, everybody. 1.11. Get it to work.
Every time I do it, I type in the same thing.
Okay. So you're going to start out with just second, then you got the square root key, which is above the
square root here, because at first I was hitting the one with the X.
I say you don't want to hit the one with the X. You actually have an X squared key there. It should be the key right above the X squared, or right on the X squared. So you got to hit second, and then the X squared key. Now what it's doing is it's taking a root other than the square root. If you're using the caret key, you want to use the X. So second X squared. And then 88 times 44 divided by 31. Because what's happening then is it takes whatever your previous answer was and it's using that as an index on your root. So you got it to come out? Okay, perfect. You bet. So now we have 1.11 square meters. Well, we're given 30 milligrams per 1 square meter. 1.1 square meters. We're going to use our proportion, cross multiply and divide, which would give us, what, 33.33 milligrams would be our recommended safe dose. So that 40 milligrams might be a little high. Now, if you're dealing with burn victims, you would also be doing a calculation for percentage of the skin covered and so, stuff like that. We're not going to get into that in here. For now, this is good enough for us. In fact, that is the complete set of information for this unit, which we covered enough in one day here. If you look on page 172 through 173, 1 through 9, the odds, talks a little bit about constituting formulas and some review of our basic dosage calculations. 178 and 179, 1 through 21, the odds, is into our IV flow rates again. Page 184, 1 through 11, the odds, deals with those titrations, minimum, maximum dosages, and not having to go through the whole calculation again. Page 188 and 190, 1 through 21, the odds, deals with the dosages based on weight and safe dosages. And finally, 196 through 197. 1 through 19, the odds, is dealing with body surface area. A lot of pages, I know, a lot of work to get done. Next week is the test. If we need to review for a while at the beginning of the hour next week, we will. Yes, chapters 4 and 5.